So, hello everyone. Thanks for joining us today for our webinar. I'll just wait one more minute maybe before we start, as a lot of people are still joining the webinar. So uh, we'll start in 1 minute. All right, let's not punish people that are here in time. I think a lot of people will join us as well. But now I want to start our webinar here about the new contingency restoration analysis that we have developed for Power Factory 2025. I'm Sebastian Palm. I'm not here alone today. Chris Dahlke is with me here. He will support me with the Q&A, as I will explain later on. And we are both from the same department. So we are from the application engineering at DIgSILENT, and our main focus is on distribution grids. So therefore, this is a functionality that we helped developing and want to present to you today. So what's the plan for this webinar? Let's take a look at the agenda. So of course, I will start with a few slides here and want to present the new contingency restoration analysis to you. So what is it made for, how is it used, what are the results that you can show. And then of course, we also will see a hands-on in Power Factory, a small live demonstration so that you can get a feeling what's possible right now and what you can also test with the correct license and so on. So in the end, there will be a small Q&A session. So the presentation and demonstration will be a bit more than half an hour, and then we will have time to answer questions. For this, we have the Q&A that you should be able to see in the Zoom tool list. There's the Q&A symbol, and you can ask questions there. So I won't interrupt the presentation, but we will collect them, and Chris will answer some of them already in parallel. So especially when there are questions for licensing, things like that. But things that we have or want to show will be shown afterwards, after the presentation here, and then we will come back to these questions. So another hint at the beginning, this webinar is recorded. So you will get the recording afterwards as well, but not before the end of next week. So bear with us a bit that we need a bit of time to post-process this, but it will be made available for everyone here. Also the presentation slides, so you will get them as well, so that you can also take a look at the material afterwards or share it with your colleagues. So those are things that will be made available afterwards. All right, now let's start in the presentation and take a look at this new functionality. So why do we need this, or why did we develop this? Well, of course, we already have a contingency analysis, but this one has been developed with meshed grids in mind. So in meshed grids, when something fails and protection trips, you often have other ways to supply it directly. So it's normally N-1 safe, or you have some predefined switch operations that will be executed for specific fault cases. However, this is not working in radial or partially meshed networks, as normally each fault or each contingency will lead to supply interruptions. So the grid is normally not n-1 safe without additional switching operations. So here, for example, this is an open ring structure that you can often see in distribution grids. And if one of the lines here has a fault, some protection device will react and will trip. However, this leads to an unsupplied area here. So we need several switching operations to resupply them. In that case, for example, this fault has to be isolated in the beginning, and then the resupply from both sides here has to be done so that the customers will be resupplied again. And these switching operations are totally dependent on the grid structure, on the location of the fault. So it's not possible to have a predefined switching operation scenario beforehand in most cases. And also what's not necessarily known beforehand is whether these resupplies will lead to some violations of constraints like voltage or loading limits. So this means we have a combination here. It's not only the term contingency analysis, because and of course we have to take a look at the consequence of faults, but at the same time we also have to investigate which switching operations are needed to resupply everyone. And so this is the optimal power restoration, which is done in the second part of this function. This new functionality is part of a module that is now called Reliability and Restoration Analysis. This is formally known as reliability analysis functions. So when you have them available, when you have this module available, then you will also directly have access to this new contingency restoration analysis. This is just a renaming here, but otherwise no change of the module has been done here. This new functionality combines functions that are present already in the contingency analysis with the reliability analysis. And what's inside? So from the contingency side, the generation of fault cases that can be done either automatically or with a predefined set of contingencies is taken from the contingency analysis. Also, that during the execution, that all the predefined or automatically defined cases are executed one after another. It's estimated which protection devices will trip or which circuit breaker will open in those cases. And the worst case or a lot of loadings and via voltages in normal state and also during the most critical failures will be recorded and then made available as a report afterwards. However, this is not everything, because we still need the part from the reliability analysis, the restoration. So, and this part is able to estimate switching operations that are needed for the resupply of as many customers as possible. And it's possible to define a specific aim for this restoration. So I will show it in the live demonstration later on, but basically you can either say, okay, I have limits or constraints, but resupply regardless. So try to really resupply everyone. And I just want to see which constraints have been violated during the process. On the other hand, you can also say, okay, you have to stick to these constraints. So I want to comply with them. And then maybe not all customers can be resupplied because otherwise loading or voltage limits would be violated. Then there are some additional options that some people will maybe already know from the reliability analysis, which you can use to modify the way the restoration is done. So I will show this in the live demonstration as well, what these options are. So one small example, it's the same structure that I've shown in the beginning. This is an example for a contingency where complete restoration is possible. Of course, you always have a state before the contingency or before the failure. So you have the normal state in the beginning, which will also be shown in result files later on, so that you have a feeling what really has changed before and after the restoration. So in the beginning, everything is fine. but then we have a fault on one of the lines, which leads to a tripping of a circuit breaker in the station here. Therefore, some customers are unsupplied, and in the last step of these trace of the failure process, we will get the notification, okay, which switches have to be opened to isolate the fault, and which switches have to be closed to resupply everyone. So not everyone can be resupplied from the normal side here where they have been supplied beforehand, but some have to be resupplied from another feeder here in this example. This may lead to voltage deviations and higher loadings, of course, but in that case, it works without any violation of any constraint. This will not always be the case. So it may also be that there are some contingencies that can lead to incomplete restorations. So when I say I want to really comply with all my constraints and limits, then this may lead to an incomplete restoration. So for example, when this line here instead is faulted, so we have a disconnection at the same point in the beginning because we only have a circuit breaker in the station typically. But the resupply now is not able to resupply everything. So the resupply will completely be done from the other side. But if this customer would be resupplied as well, this would mean that some constraints, either voltage or loading or both, would be violated, and therefore those customers not resupplied. This depends now on the main target that you have selected in the command. So when you said, okay, restore the power regardless of the constraints, then this one will always also be resupplied. But here, when you consider the constraints, then you will get a message or get a report in the end that shows, okay, for this contingency, not everyone could be resupplied. So of course, you don't want to have to take a look at each contingency individually. So you normally will calculate a lot of contingencies at the same time, one after another, of course, but you will get an overview over the results already in a single line diagram. So here, in that case, we calculated contingencies for all lines in this grid. And according to the color, we can estimate what happens when a contingency happens at this element. So of course, easiest one are the green ones. So when one of these elements is shown in green, this means there's a contingency that leads to a tripping of protection. A complete restoration is possible without violating any constraints. Of course, this should be the case for the most parts of your grid. So you hope that almost everything is displayed in green, but there may also be other cases. One of them that is shown in purple here. This means that the restoration is not possible when this element fails, as there's no other topological way to restore the power. So this station here, for example, only has this line as a connection. So if this line fails, of course, it's not possible to resupply this customer here. So those are topological maybe problems or ways for improvement that you can see with this color. Also, very easy to explain is the red color. So this means it would be possible to resupply all customers, or it is possible, but only with violations of constraints. So when this line fails, this means topologically, we are able to restore the power to our customers, but in this process, a loading or voltage limit will be violated. So there's also room for improvement. And then, of course, we can have the combination of both. So when we cannot resupply some customers due to topological reasons and some due to constraints that would be violated or are violated during the process, then we will get the pink color here. Of course, those are just the default colors. So as with every color legend in Power Factory, you are free to change the colors according to your needs. This is just the predefined version of the coloring of the single line diagrams. It's not only possible to show results in the single line diagrams, but we also have a lot of reports that can be generated. A very important one here is the contingency summary. So this is really an overview over all contingencies that have been calculated, and will give you an overview, okay, what was the effect in the beginning? So when this contingency happened, which power has been interrupted, how many customers have been interrupted, though in the beginning, but then it will also tell you, okay, was it possible to restore everything? Or maybe not. So here there are some cases also where not everything could be restored. And now it depends also whether you allow violations of constraints or not. In this case, violations are allowed. So it shows you here that there are some cases where everyone can be resupplied, but only with the violation of some constraints. Also shown here are the number of switching actions that are needed for restoration. The less, the better, of course. I will show you a way later on to limit this as well. So this is really an overview to get a feeling, okay, how many contingencies are there that may leave people unsupplied in the end. You can take a closer look at specific contingencies and open their restoration report. This will give you an overview over all switching protections. You will see the protection devices or the circuit breakers that opened to react to the fault and to a trip. And afterwards, you will see all switching operations that have been estimated by the power restoration to restore the power, but also to isolate the fault, because in the beginning, the fault has to be isolated and then the restoration here is done. So you can see all these switching operations for each contingency. So this is then just a list where you have these switching operations for each case. There are a lot of other reports, one or two I will also show in the live demonstration, that focus more on the loadings and voltages that happen before and during the contingencies. There are several different ones that can show these values per element or per contingency. When you have already worked with the contingency analysis, then a lot of those reports will be very familiar for you. If you want to look closer at the results, you are not bound to our reports. Of course, they can also be modified, but you can also access the result files. And there are 3 different result objects that are produced while a contingency restoration analysis is executed, and they contain the calculation results. So the load flow result object here really records the load flow results at the end of the restoration for each network element and each contingency. However, it will only record values that exceed recording limits that have been predefined. So normally this will be a sparse matrix, so not every element will be filled in. But if you set the recording limits very low, of course, then it will store everything. Yeah, it's just a way to keep the data usage here not a bit at the minimum. So this can be adjusted by the recording limits that I will show later on. The second one, the restoration result object, contains the information about the restoration process, basically from this overview report that I've shown to you. So it will include the switching operations that have been estimated, and also how much load and how many customers have been interrupted and how many are still interrupted at the end of a contingency. So those values are also stored in this result file, and you can work with this later on. And then you have the summary, which contains the extreme values for voltage and loading for each network element and the contingency where this happens. So this is really a summary that only contains worst case values. And these files can be used, as you know, from other functionalities with scripting. You can export these files and post-process them. So they give you a way to post-process the data on your own if you want to make further studies. Okay, enough of the theory. Let's take a look in Power Factory at the contingency restoration analysis. We prepared a small project here. So distribution grid here, which is supplied by two transformers here. So from the 110 kV to the 20 kV, we have different feeders that are shown with different colors here. So this is one of the things that is needed also to execute the contingency restoration analysis. You need to define feeders. And also a thing that is needed, you need to either define protection devices, or at least, and this is the more common way, I think, is that you have defined circuit breakers in the station. So when I take a look in the station here, then you can see that at the start of the feeders here, we have circuit breakers, because those elements will be used to define where the protection zone ends and which switches will trip during a contingency. So this is our grid in the beginning. Yeah, you may also remember this open ring structure here. This is what I have shown you in the presentation. But right now we have no results. It's only a coloring according to the feeders here. So now let's take a look at the contingency restoration analysis. So maybe start here. So it has its own toolbar here, the contingency restoration analysis toolbar. And we will look through the icons. The most important one is, of course, the first one. This is the commands to execute the contingency restoration analysis. As basis for this, normal load flow calculation will be used. So as you know from other functionalities, you can also adjust the parameters for the load flow that is used for calculations during the contingency restoration analysis, but those are known from the normal load flow. So also a very important part is which contingencies shall be used. And an easy approach would be here to let Power Factory create them for you. So you can either automatically create them when the calculation is started or before the calculation is done. And you can also say, okay, which elements shall get contingencies. So in this example, I'll stick to lines and a few additional cases as I will show you. And you can also limit the selection. So when you say the whole system, then really everything in the project is considered, but you can also say user-defined, only elements of a feeder, only elements of a specific zone. So you can limit the investigation. You don't have to calculate it for your whole grid every time you execute this command. You can also put some additional fault cases here. So in addition to the line faults, I predefined here some busbar outages at the station, so they can be considered as well. So you can also have a mixture of automatically defined contingencies and manually defined contingencies. Also, so this is a process that you may already know from the contingency analysis. So in the protection, we have to tell the functionality what shall be used for the tripping. So in the most basic case, you just say, okay, each circuit breaker that is modeled can be used as the end of a protection zone. If you have modeled protection devices, then you can also switch this, that only switches where the protection device is modeled shall be used. In most cases, using the circuit breakers will be fine. And the very central part here is the restoration process. As I already told you, there are two different main targets. So the first one, maximize restored power, means that every switch operation that is useful to resupply a customer will be done here, even if it violates constraints. So in the end, you will get a notification. Okay, there are some constraints that have been violated, but here you will really say, okay, this is fine. I just want to restore as much power as possible. On the other hand, you can also comply with constraints. Then the optimal power restoration will stop once the next switching operation would violate some constraints. So this is a way to always stick in the limits and to see, okay, how far can we go without violating constraints. We will start here with the maximizing the restored power, but I will show you the difference as well. So the tie open point optimization means whether the tie open point can be moved either with or without load transfer. Without load transfer means in the outage feeder, it's okay to move the tie open point. When you switch to with load transfer, as I will do in the end, then it's also possible to move a tie open point that needs a short interruption of customers that are normally not affected by the contingency. But it will give you more possibilities for the resupply. Busbar transfer means whether simple reconnection, this means only adjacent busbars may be connected during the restoration, but you can also say this should be optimized and more complex changes of the switching configuration in stations will be done. And you can even allow additional measures. This would mean that it would also consider, for example, parallel operation of transformers, which are normally not done. So in backward recovery means whether you can restore the power of a station that normally has no more supply. So you can restore a station or from a station by another station. So this is a very sophisticated recovery process. Normally it's not allowed, but in case you are allowing it, or if you will take it as a measure, then you can of course also allow this here. You will also find the selection here to limit the number of switching operations. So when you say, okay, I will see how far can I go with, for example, 4 switching operations, then this is a way to limit this here. By default, it will use as many switching operations as necessary to find the optimal solution. Then there are constraints, also a thing that is known from a lot of different functionalities. So we can have thermal loading constraints, voltage constraints, which means absolute constraints in the end, and also voltage drop and rise constraints along a feeder that can be used either globally. So in those cases here, we have global constraints, but you can also say, okay, those are individual values. So when you, for example, have a differentiation between cables, overhead lines, transformer loading constraints, then you can also define this in the elements themselves. But in this example, we will stick to global constraints with a maximum loading of 100% and voltage limits of 0.9 and 1.05 per unit. The last step here is regarding the recording of results. So I told you that not all results are stored, but only when they are above specific limits. So when you want to really have all end states, then you can they can change these values to very small values so that everything is recorded. By default, this is done in a way that the data storage is not too large in the end. But the worst cases are already stored. So the recording limits will not affect the worst case situations that are recorded. Okay, now let's execute it and see what happens. So as you can see, we now have a coloring here, and I'll maybe increase the size here a bit. So everything that's green, that is fine. So everything green means if this line has an outage, then we can resupply all the customers without any constraint violations. However, if it's red, like those lines here, this means we can resupply all customers when one of these lines fails, but we will violate some constraints. And we also have the case, as you can see here, that there are some customers that cannot be resupplied when this line fails, and there's simply no way to resupply them. So when this line fails, then we cannot change the switching state to resupply them. So this is what we can already see here just by taking a look at the colors. So let's see how this can change. So I added a small new connection here. So at the moment, we cannot resupply them. When I add a line here in a variation, so now I have a second line from the other side and execute the functionality again, then we will see this new line gives us a way to resupply these customers so that these lines are now also displayed in green. So this really considers the topological state of your grid and will consider the ways they have to resupply everything. When we now want to look at specific contingencies and what happens there, we have the possibility to look at the trace here. So let's take a look at one of those lines that we improved right now. I think it's this one here. So this in the beginning, you have a base state. So in a normal state, normally you shouldn't have any constraint violations. And then in the first step, it will show where the contingency happens. So here, this line has a fault. And you can also see with the red circle here that this circuit breaker trips. And therefore, this area, this feeder here is outaged. And in the last step, it will now show me the necessary switching operations. And as you can see here, it will open these two switches so that this fault is isolated, and it will do a resupply from this side and also from this side, as these two stations can only be resupplied from this side. So this also already gives us a graphical representation, and we can take a deeper look into specific contingencies when you want to see what happens there. But of course, we also want to get a feeling and overview of this over this. Therefore, we need some reports, and they can be produced with this element here. So there are a lot of different reports available. I will just show the worst cases here and also the contingency summary, which is a very useful report, but there are a lot more that we don't have enough time to talk about. So let me just show you a few of them, and let's start with the contingency summary. So this is a thing that I already have shown in the presentation. So for each contingency, we can see here, okay, how many customers have been interrupted, what was the interrupted power, also what is the state in the end. So this is one of the contingencies where we were able to resupply everyone without the violation of constraints. And we need 4 switching actions for this. But as you can see here, we also have other cases like this one, where we cannot resupply everyone, but we don't have constraint violations. So this means here in that case, a topological problem will be the reason that these customers or this one customer cannot be resupplied. If we want to take a closer look at an outage, let's take again this line here. We can right-click on it and open here and open the restoration report. And here we can see all the switching operations, so which circuit breaker reacted, which switches have been opened, which have been closed. And this is available for all contingencies, so you can take a look at all restoration processes here. Then, of course, also we want to take a look at the worst loading violations. So here we can see, okay, this is the line with the highest loading, and we also see which contingency is the reason for that. So here with the 3 highest ones, we already see that this contingency here seems to be quite a critical one. So this gives us a feeling, so which line should be reinforced, or where we should take a look how a restoration could be improved in those cases. We will always see the base case and the contingency case, and the difference here also have this as value, so that we see graphically here where it's critical. Of course, we also have a lot of elements that are never critical and will never exceed their limits. The same is available for the voltage. So let's put the voltage limits to 0.9. Here we also see that in the beginning, in the base case, a limit is never violated, but during contingencies, it quite often happens that there are some violations of the thresholds. Okay, so this is what we can see here. And this is when you maximize the restoration. However, there's also the possibility to comply with the constraints. So in a second execution, I will comply with the constraints. And this means now the colors change a bit. This means now in this pink case that we have constraint limitations. So here, the constraints will not be violated as we stop the resupply before constraints are violated. This can also be seen in the report. So when we create report again, then we will see that there are no violations of voltage or of loading, as we set as aim that they shall not be violated. However, our contingency restoration will show us that there are more cases where there are still unrestored power and unrestored customers in the end. And here's also the notification. Those cases could not be restored completely because constraints would have to be violated to continue the restoration. This limitation also often needs more switching operations because more feeder optimization and things like that are necessary. However, it really gives you an overview of which fault cases are completely uncritical, but which are also maybe not optimal at the moment. So using the heat map, we see, okay, there are a lot of fault cases here that cannot be restored completely, but we still have options. So we can still look at our restoration process. So for example, if we allow the tie open point optimization, even with load transfer and execute it again, then we already see, okay, there are some measures or some ways how to do the restoration that could improve the behavior even without changing the topology, for example, or without changing any equipment. So sometimes maybe you have to rethink the restoration processes, and this is also a thing that can be compared with this tool here. So, all right. This is about it. Just a few final remarks. So hopefully I could show you the new functionality. And if you want to take a look on your own, you have this license available, then you can already, in Power Factory 2025, take a look at the application example, medium voltage distribution grid. This one already has a study case that is about the contingency restoration analysis. So here under File, Examples, medium voltage distribution grid, you will see that there's a video and also the project available to do or to try it out. All right. So the new contingency restoration analysis, to sum it up, enables an investigation of contingencies and their consequences, also for radial and partially meshed distribution grids, which is not possible with the normal contingency analysis. It is easy to use it in existing grids. So the only thing that is required to use it are feeders and circuit breakers, so that the tripping and the restoration is possible here. But in most distribution grids, they are already defined, so it shouldn't be too many changes you have to do on your projects. We also have extensive options for visualizing the results. So have the different coloring. We also have the table reports that are only scratched the surface of. So, and you also have the result objects that you can use for post-processing. Of course, this is a new functionality, and we will still add new things to this. It's still in development. So two larger topics that are developed at the moment, of course, always without a guarantee, but I was told I can already say this. We want to add a new constraint because sometimes the problem is that you have a compensated grid and you also have to consider the compensating current. And so limiting the capacitive current for the new supply areas is also planned as a new constraint that can be used according to the available coils. And also, some people may already know from the contingency analysis that you can load existing results so that you don't have to recalculate everything when you want to take a look at the results. This is would be an easy option to just restore the results. All right. Thank you for your attention. Now we still have 20 minutes to answer questions if there are any. And I'll just give over to Chris. Did you already get some questions in the Q&A?
Thanks, Sebastian. There were two questions now, or just one came in. I basically just left them open because I think they're good to discuss. Maybe we can go to the first question, I think, which you might have covered briefly. So from Alan. It's in the N-1 contingency analysis, what level of switching actions for restoration of supply will be considered? Will it simply be resupplied from an adjacent feeder, or will the system shift load from adjacent feeder to a third feeder to avoid overloading of the adjacent feeder when restoring supply after the original fault?
Yeah, that's a good question. Yes, so it will not only do a simple resupply, it really will take a look at all all options. So of course, often the easiest way is just to move the loads to an adjacent feeder, but it will also, if you allow a large number of switch actions, because you can limit it, but when you don't limit it, then it will also consider third or fourth feeders that may be optimized so that a restoration is possible to stay within the limits. And especially when the option to enable the tie open point optimization with load transfer, when this is activated, then it will have a lot of possibilities to optimize the restoration without violating any constraints. So there's when you are not limiting the number of switching operations, there's no maximum level that can be used here.
Yeah, so I think, yeah, as Sebastian said, that's possible with these options. It also goes the other way around. If you want to have like a minimal amount of switching actions, you can also like disable all of these additional options we have there and just see, okay, what minimally could be achieved basically when you
Yeah,
disable all of these options.
yeah, when you exactly, yeah. So this would be the most basic settings here. At least a bit of tie open point optimization normally should always be activated, as really gives a lot of options here. But yeah, so you can also stick to the minimum of switching operations. But of course, it will always try to find the optimal solution with as less switching operations as possible.
Yeah. I think the only thing that's not allowed, if I remember correctly, is you don't interrupt one load that is not affected by the original contingency to allow more restoration in another feeder, I guess.
Exactly. This is the
Yeah.
case when without load transfers
Oh, yeah.
activated. When with load transfers
Ah,
activated,
true.
then it will consider also interrupting loads from not uh, faulted feeders to be able to restore more load in the end. So it will restore them, of course, as well, but it will allow it to also move them around so that they may have a short interruption.
True.
Yeah.
All right. So yeah, I hope the question was answered. Then we go to the next question. Um, if you only include cubicles at each end of your feeder and have not modeled switches circuit breaker, will the module still work?
Unfortunately, it will only work with circuit breakers. However, um, I think this is not possible here. When you have these star switches, let's just create one of them and some busbar. Let's see what that's possible here. Um, do I have some here? Here. So star switches, those are the switches that are stored inside cubicles, and they can also be defined as a circuit breaker. So also only using the cubicle arrangement could be used here when you change the switch type of these normally logical switches that are stored in cubicles when they are changed to circuit breaker.
Yeah. So every time you see like this symbol there of the cubicle, that cube, at the end of the line, then you know a switch is modeled there, if it's like modeled out or just has an internal switch, and these can be considered.
Yeah.
And in the switches that Sebastian showed, there's also then the page similar to this one here for the contingency restoration analysis, where you can basically decide if it can separate a fault or if it's used for the power restoration. So I think by default,
Exactly.
they're
Yeah,
all allowed.
this is the default value exactly. So they can be opened to isolate a fault, but you can also, when you say, okay, the switch shouldn't be used to isolate a fault, then you can just untick it. And then this may lead to more topological constraints, of course, when not all switches can be used, but in reality, you may have some switches that should not be used for the opening and may also should not be used for a resupply, but this then really depends on your needs. By default, all switches can be used for the opening and the resupply.
All right.
Okay.
I hope we answered this one as well. Then we come to the last question that is in here by now. Again, for all of the others, you have still time to ask your
Yeah.
questions. Yeah, the next question was if you can explain the backward recovery briefly again.
Yeah,
Just,
yeah, I
yeah.
was a bit quick on that one. So this means when you have modeled several stations here, the when I not only have this one, but another one as well, um, then the backward recovery would be a possibility if, for example, the contingencies here are of these transformers. So this may also be the case that maybe only one of them is in service and the other one has an outage. Then normally we would have no way to resupply any customers here in this grid. But when I allow a backward recovery, then this means I can come from another station that may be located, for example, here, and I can resupply this station from another station and then use this to resupply the feeders in this grid. So this is in the end, this means coming from another station and resupplying a whole station and its feeders. This is normally not allowed as it's a very specific application, but if this is an option for you, then you can allow this backward recovery, and you can also define whether it should still a standard recovery should be preferred. You want to prefer the backward recovery or want to have a user-defined preference per station.
Yeah, I think we also have an extensive description of that in the user manual if you want to look it up, but I hope that was.
Yeah, so I also opened it here in the end. So always remember when you're looking at for a specific part in the user manual, you don't have to search through all of it. Just open the command here and press F1, and this will automatically open up the user manual at the position where the command is explained. And all settings in the command are explained here, and especially the restoration options, as they are not as easy to understand, have a longer explanation here, and also the backward recovery is explained in the chapter reliability assessment. There are also some figures that will explain this a bit further. So let's see here. So yeah, so that I think this would be a possibility to get more information about these settings as well.
All right, we had 4 more questions coming in.
Oh, okay.
5 now, so we have some stuff to do. Yeah. So, what would be the easiest way to allow only certain switches to be considered in the restoration process? For instance, if you want to differentiate in between manual operated switches and remote control switches.
That's a good question. So compared to the reliability analysis is a bit different. So in the reliability analysis, also things like remotely controlled or manually controlled are considered because they have different times. But the contingency restoration analysis does not consider how long it takes to change a switch or to have a switch operation. It will only search for the best solution of switches. So to consider or not consider them compared to the reliability, where this has an impact in the contingency restoration analysis, you can only say whether you want to allow it to be used or not. So if you say, okay, in the process or in your planning, when you look at these N-1 cases, for example, then you only want to consider remote control switches, then you have to untick that other switches can be opened or used for the restoration here. So those are the things that have to be changed in the switches so that they are not used during the restoration of customers. Of course, this will in a lot of cases lead to a lot of unrestored customers when you cannot tackle down the isolated area to the last line.
And I guess the easiest way to configure that is via the network model manager, where you can filter after, let's say, remote control switches with the corresponding parameter and then configure it via this.
Exactly. Yeah, that's a good hint here. So of course, when you already defined this for the reliability, these settings, then you can, as Chris said, you can use this to filter this. So for example, when I have some Yeah, here some of them I have said, okay, this is remote controlled, and another one is only manually controlled, for example. Then I can use the network model manager, say, okay, filter, and I only want to see manually controlled switches. There's only one in that case, of course. And then you can switch to the contingency restoration analyze page and can now just copy and paste the settings so that they cannot be opened and maybe also should not be used for the power restoration. So you can just copy and paste these rows or these cells in the other rows. This would be the fastest way to do this.
All right, next question.
Yep.
First, a compliment. Thank you for the insightful presentation.
Thank you.
And then in scenarios where certain loads are deemed highly critical, shouldn't contingency plans prioritize restoring those loads first to minimize operational or safety risks? Should
That's
we consider that the critical loads should be restored first if the contingency occurs?
Yeah, that's a very good thing here. This is possible. So of course, when you say maximize restored power, this does not matter, as all loads that can be resupplied will be resupplied. But when you comply with the constraints, then one thing that I haven't mentioned yet, then a new setting on the advanced pages will show up. You can then say, okay, which load priorities shall be used, as each load has a load priority parameter. So this is a thing that's also used for the reliability already. So that's not a new setting. So when you take a look at a load at the contingency restoration page, you see you're not only saying how many customers are supplied here, but you can also give it a priority. And then the algorithm will consider this, and you can just say, okay, is a higher value of the priority the most critical, or is a lower value the most critical? Because the definition is a bit different between grid operators, but this is a thing that can be considered in the resupply here. Yeah. Thank you for the question. I forgot that.
Yeah, very good. Next question is, you mentioned that feeders are required for the tool. In the tool, is it specified that they are required? Are there any requirements for the feeder? Do they need to be radial?
Yeah, so the tool will give you a hint when there are no feeders that it cannot do this. So there's a warning message. In some cases, it will automatically create temporary feeders. So when there are very easy arrangements where feeders are missing, then it will auto-create feeders. So it will try its best to even make the calculation possible even when you don't have feeders. But the best case, of course, is that you have them predefined. In the end, it's not that hard to do it. So just right-click on a bus bar, take a network groupings feeder and new, and it will create feeders for all outgoing lines. So this should be a thing that's hopefully quite easy to do. And yeah, and they don't need to be radial. So when I have a closed feeder somewhere, then of course it will still work. Yeah, so this is also working. Then several for example, let's see when this line here, when this line has a contingency. Let's take a look at it. Then this means because it's a ring structure, several circuit breakers have to trip. So more customers will be outaged in the beginning, but it will then find a way to resupply them as best as it can. It won't recreate the original structure, as this is seen as an emergency resupply in the end. So it will try its best, but it can also work with ring structures and meshed grids. Of course, if you have a heavily meshed grid, then maybe the normal contingency analysis with specific arrangements or remedial action schemes is a better way to go. For distribution grids with slightly meshed or ring structures, it's working, of course. Yeah.
I guess that was one of the main focuses of the developers, also for some other tools to allow this.
Yeah.
It's common.
In the reliability, it's also available from 2025. So you can also calculate ring structures and meshed or bit meshed grids with the reliability functionality. So this functionality has been improved as well with 2025.
Yeah, thanks for the question. So we have two more. switching happening in case of the contingency analysis. So I guess the normal transmission contingency analysis, are they different from contingency restoration study?
Yeah, so a bit in the end, the tripping will be the same. So when you have a contingency somewhere, it doesn't matter whether you calculate this contingency with the contingency analysis or with the contingency restoration analysis. However, the normal contingency analysis will not do the resupply automatically. So of course, you can resupply some schemes that will take effect when some bus bars outaged, for example. So you can predefine what shall happen in case of an outage, but this is not calculated during the runtime. So here, the advantage here is that the algorithm itself will estimate what are the necessary switch operations after it's tripped. But the first step, of course, the tripping of the protection devices, this is the same as it is in the contingency analysis.
Yep.
All right. One last question.
So we have
Also,
one more question, yeah. After doing a restoration analysis, results can be shown in the network model manager. For lines, there are variables for base loading and max loading in all restorations. There can also be shown an ID of the contingency which causes the maximum loading. What is the ID referring to?
so let's take a look. And line, max loading, and I don't know what the parameter is called specifically. So the idea has to do with the contingency itself, as during the execution of the contingency restoration analysis, each contingency will get one of these IDs.
So I
However,
currently also don't.
max contingency. Okay.
I assume they just get a number, and that's the number they also refer to in the result file, since the result file can't store any strings or objects, but only numbers, and I guess that's the ID that they get.
Yeah. Yeah. So to get the specific contingency for those cases, you will have to take a look in the result objects. There, the names of the contingencies are linked to the contingency numbers.
I guess
Right.
similar, it should also work for the other contingency analysis.
Yeah. Yeah.
Yeah.
All right. 2 minutes until 12. So we would have time for one last question. But if everything has been answered, that's fine as well. Okay, great. Then thank you for your participation here. I hope we were able to show you this new functionality and how it can be used, what you can do with it, and could answer some of the questions. If there are questions later on, of course, feel always free to write me, write us, also over the support. That's always a possibility. And again, you will get the material afterwards. So the presentations and the recorded video will be sent to you, but not before end of next week. So you don't have to ask for them. You will get them regardless. So
Yeah, thanks also from my side. And yeah, as Sebastian said, your feedback is always welcome. So when you have a look at the functionality, just give us feedback on what's maybe missing, what you like, so we can further develop this new functionality.
all right, then thank you and have a nice day.
Thank you.